All right, so welcome to the tutorial session. This is in order to prepare a little bit for the symposium that we have on Friday. And the idea is really to show that when you look at complex systems like in fluid dynamics, and then you look at applications in climate, it's really that you draw from different field of mathematics. You need to know about stochastic systems, you need to know about partial differential equations, and then there are a couple of sort of specific ideas and results that are important just as a background for understanding what's actually going on these days. And what I've planned for this tutorial is I will start with a sort of general review of very quick probability theory and stochastic dynamics. One of the focuses will be to talk a little bit about alpha stable distributions and Levy motion. That might be a lot of the things at this first part you might already know or have seen it before. But if you haven't seen alpha stable distributions, that might be hopefully of interest to you. And then we'll talk a little bit about the connection of those stochastic systems to fluid systems. And this will sort of, again, set the scene for Friday. This is, especially since we are a fairly small group, this it's nice to make it very informal. So at any point in time, please jump in, ask questions. Yeah, just sometimes if there are no questions, I tend to talk faster and faster and faster. So interrupt me, make me slow down if necessary. And again, just let's try to make this sort of an interactive tutorial. So what I'm going to do is I'm going to share my screen for most of the time where you see these little notes. But then here or there, I will comment on those notes, write on that virtual paper, or switch to the whiteboard. And I will also demonstrate a couple of ideas using Matlab. If anyone is interested in the Matlab codes, you can just email me and I'll be happy to share them. If that is something that where you want to play a little more or see how this is done, just email me and I'll be happy to share this. So to start off, I want to take you back to the basic world of random variables and probability distributions, something that you've certainly seen many times before. And when you talk about a random variable, then the funny thing about random variables is that you look at their range. So you look at the set of values that the random variable can take. And there are in principle two different kinds. This set of values that the random variable can take can be discrete or it can be continuous. And what happens is that, again, this sort of slightly maybe when you see it for the first time, you might remember this slightly confusing notation where you try to assess the probability that the random variable can take one of the values. Yeah, so often we then, for instance, we just say pi in a discrete case is the probability that the random variable takes one of those discrete values xi. Okay. And typically what is happening is that it's some of the cases are very easy, like you roll a die once, then obviously all the outcomes are equally likely and all these probabilities 1/6. The probabilities always add up to 1. That is just written as a sum of all the probabilities. And then one of the, we can start to define more complicated projects. So for instance, the mean is the weighted average of all those values. So the values are weighted with the probabilities. And if you look at continuous random variables, then of course what happens is those sums, they become integrals. And in most, I think everything that I'm going to talk about today is whenever I assume that we are looking at a continuous random variable, I actually assume that there exists P of X, which is a probability density, okay? You can develop this in a slightly relaxed assumption, but I'm not going to do this today. We always have a probability density that we can work with, okay? Now, this one of maybe the most basic examples is that you look at the sum of sum of the points, you roll 2 dice, and this sort of illustrates what the probability distribution really means. Like for instance, if you want to figure out what this probability is, then you need to form the inverse image of this event. So in this case, for instance, this would be this set of favorable outcomes, in this case 6. And now you can sort of see that if you start to graph the associated probability distribution, of course, if you look at the sum of the dice, you get a triangle, yeah? And because at every time you move to, like this, for instance, would be the case for x equals 8, the sum of the dice would be 8. And you see that this is, and this would be for the sum of the dice being x equals 6. Yeah, and so the probability here distribution would be a triangle. Now, these things, obviously, when we talk about these kind of distributions, then we can easily simulate these things on a computer. And this is the idea of Monte Carlo simulation. So let me just share. Can you see the Matlab screen? Yeah, all right. So, and of course, I forgot to copy one program. Just give me 1 second. Okay, fantastic. So the function 1 die just rolls the die 1 time. So if I just do this 100 times, then I can obviously just create a histogram and create a bar graph. And you clearly get a uniform distribution. Can you see the graph? Yeah. So in this case, if we want to do this with 2 dice, we can just modify this program easily. Now our range is from 2 to 12. And here we go. And one interesting thing is that if you if you look at a couple of realizations of this, you see that some of them they sort of look like the triangle, but there's actually quite a bit of variability here, yeah? Maybe one more. Now look at this. So if you're into board games, then there are a lot of board games that are based on rolling two dice and looking at the sum. And I think one interesting aspect of those board games is that on a typical evening, the distribution is not necessarily that triangle, yeah? And this sort of gives you a feel for, while in the limit, of course, if I really go high, I go to 10,000. I get pretty much this triangle. In reality, if we, for instance, talk about scenario analysis and the risk of floods or things like this, it might be really costly if you want to really predict these shapes, especially if the distribution is not Gaussian. Now, anybody has an idea how I can make this more Gaussian?
Take more dice.
Take more dice. That's exactly how it works. So there's this program MDice. That do exactly this. So for instance, like let's take 10 dice and roll them 10,000 times. And up. If we do this, you will see up. Something happened. Well, let me see. You can see this looks already like pretty much, well, somewhat Gaussian, yeah. So in some way, if you look at these dice, this is the way to the Gaussian distribution. You start with uniform, then you get the triangle, and then as you go along, eventually you get a Gaussian. But it also gives you a feel for if you actually want to really get sort of the tails of a probability distribution, you might not estimate those, but actually get them from your multicolored simulation. You might actually need quite a bit of data in order to do that. And obviously, sort of there's this whole idea of estimating rare events and figuring out how to do this. This is one of the things that research-wise I'm interested in. Now, just going quickly through the standard probability stuff to remind you, obviously the most basic idea is to flip a coin. And if you do this many times, then obviously what you get is the binomial distribution. And I think I forgot to share. Now you should see, can you see the lecture notes again?
Yes.
Okay. So binomial experiment is basically you have up or down or success or failure. What happens next time is independent of what happened before. And then if you just look for your random variable as the counting the number of successes, then obviously you get this binomial distribution that is written down here. And similar to the dice, if you perform this many, many times, what happens is that this binomial distribution approximates a Gaussian distribution. And one of the things that is important is if you are in this situation, the mean is simply given by n times p, and the variance is given by npq. And there are different ways of doing this. By the way, again, especially at the beginning, you might have seen this many times. I sort of write a little ex in parentheses. So if you are interested, these are points where if you forgot how to do this, you can sort of try to derive these things as a little exercise. These formulas are can be derived in all kinds of different ways. You can use properties using those binomial coefficients, but what is a little easier is to figure out that for one trial, the mean is just p, and if you add up random variables, you know that the expectations just add up. Yeah, so for n trials, you will get a mean of np. For the variances, one has to be a little bit more careful. Here you have the definition again of the variance. The variances of random variables only add up if the random variables are independent. And also, since the variance is a quadratic quantity, you have this kind of shifting properties that I just want to remind you of, that if you have a factor here a, then obviously because of the quadratic nature of the variance, you get an a squared here in this shifting formulas. Okay. Any questions up to this point? Probably you know all of these things, yeah? Any questions? All right. So the last little ingredient in the probability review is to talk about the Gaussian distribution. So the Gaussian distribution, again, very naturally appears if you just add up random variables. We've seen this just for the dice. Just add it up, you end up with the Gaussian. And I just reminded you that for the binomial distribution, that also happens. Yeah, you just add them up, you add up enough, you get something very close to a Gaussian. So this is why the Gaussian is so incredibly important. And it is also very nice because it basically has two parameters, which is the standard deviation and the mean. And obviously, if you now just take this distribution, put into the formulas of variance and expectation, you will retrieve obviously the variance and the mean. Now, if for the dice, if you didn't have really a chance to look at this code carefully, but if you look at the code carefully, then all you need to do is you just draw a uniform random number, you multiply it by 6, and then you just take the ceiling. It's very easy to draw, in this case, a random number. For Gaussian distributed random numbers, this is a little harder. It's actually a really nice calculation. There are many ways of doing this, but one of the standard ways that always is given in lectures is the so-called Box-Miller algorithm. And you might have seen this before. If not, that's just certainly something that would be interesting to look up as sort of the general knowledge. The way it works is you draw uniform random numbers, draw 2 of them, and then you just put them through this transformation. And you see there's some polar coordinates, something plays a role. And if you do this, you simply get a standard normal distribution. And then, of course, if you need some different mean or variance, you can easily scale them. You know? This just shows how, in principle, it's really easy to generate normally distributed random numbers from a uniform distribution. And again, they're, if you take as a 0 iteration some book on numerical methods like numerical recipes, you will get some idea of how to do this, but there are actually more efficient ways of doing this. Anyways, this is sort of one of the standard ways of generating random numbers that you might have seen. And then one of the interesting associated functions that we often look at when we look at random variables is something that in some way can be interpreted as the Fourier transform of the probability density. Yeah. So if you think about this expectation, if you write this as an integral, is of course nothing else but the integral of e to the I s x p of x dx, yeah? And that gives you the Fourier transform of the distribution. And it's, again, an easy exercise. You basically just complete the square of a Gaussian integral to verify that for a Gaussian, the Fourier transform is again a Gaussian. So in particular, for instance, for the standard normal distribution, you just get e to the negative s squared over 2. And you also know that if in the original formula you have the variance sit here, yeah, that means if you have a small variance, your Gaussian will be very peaked. Then in Fourier space, obviously, it will be very broad. Yeah, what is, and yeah, depending on what the conjugated variables are, yeah, whenever these sort of always behave in inverse form. Yeah, whatever peaked in time domain is broad in frequency domain. Yeah, or if you think of quantum mechanics, yeah, that's in some way some form of the Heisenberg uncertainty relation. Yeah? So these are in some way the little ingredients that I wanted you to remind you of in the realm of probability theory and basic statistics that we can use to go now a little bit further. Are there any questions up to this point? All good? All right. Just as a sort of quick check, who has seen alpha stable distributions before? All right. So now the sort of the real story begins. What happens is that Gaussian distributions, they somehow decay fairly quickly. Yeah. So and it seems totally natural that those are the governing distributions because of the central limit theorem. Yeah. And again, if you think about the binomial distribution, or if you think about the dice, you just add up random variables, and if you add up a sufficiently large number, you end up with a Gaussian distribution. Okay, but there's a caveat. There's actually a mathematical condition that proves to be really interesting and really important. Does anybody remember what is the condition what is the additional assumption that we need to make for the central limit theorem to actually hold? Central limit theorem in the original form, which we just add up independent, identically distributed random numbers, and you end up with a Gaussian. When does this not, what is the condition for that to be true? The random variables need to have finite variance. And it seems to be a very, 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 maybe very unimportant condition. But then a while ago, Paul Levy thought, well, what is if this is not the case? Can I look at random variables where this assumption is somewhat violated? And one way to do this is to break analyticity in Fourier domain. And this is how this works. So when you specify the characteristic function here, can you see again the lecture notes? Then obviously you specify also the probability density, because what you can do is, again, I'm sweeping a lot of math just under the rug here. Yeah. So there's certain assumptions where you can do this, but most of the time, under fairly mild assumptions, if you know what the characteristic function is, you just Fourier invert and you get your probability density. Okay. Now the Gaussian s squared e to the negative s squared will be mapped back into the Gaussian. What happens if you break analyticity around 0? And here, this is one way of doing this. You just put, instead of a square here, absolute value of s and a little alpha. Now, you cannot in Fourier invert in a super nice way, meaning that if you now try to compute the inverse Fourier transform, it's not going to be, there are only special functions that you can use to express this, unless alpha is 1. Yeah, if alpha is 1, then that's a standard little exercise. It always happens if you take complex analysis and you, it's one of the really nice calculations of residues. If you invert this function, you end up with a Lorentz or Cauchy distribution. And now you see how this works. The Cauchy distribution, this guy here, if you try to compute the second moment, so something like integral x squared px dx, then because you only have an x squared here, it will not converge. So this is one of those examples where actually the central limit theorem fails. And there's a whole class of alpha stable distributions that Levy, if I recall well, discovered. And these distributions are interesting because they have heavy tails. And recently, since people discovered, for a lot of phenomena, this idea, everything is Gaussian, let's get some data, let's fit mu and sigma, and then let's extrapolate to the tails, just doesn't work, because the tails do not follow a Gaussian distribution. And if you use this sort of idea of approximating a Gaussian, you might underestimate the rare events, the likelihood of rare events, not by a factor 2 or 3, but maybe by a factor 10,000. So the people recently got really interested in these kind of distributions that give you a little bit more flexibility, in particular in modeling distributions that have algebraic tails. And so there's a way to, while you can't really Fourier invert the characteristic function nicely, you can actually figure out what the asymptotic, what the decay is of those tails. And it turns out that they have algebraic decay. Okay? In simulations, like for instance, if you have any Matlab code set up and now you want to switch to those distributions, that is actually really, really easy. So now, of course, Matlab or Python libraries, they have routines that do this, but I just want to emphasize that you only need, there exists a box Miller-like algorithm to simulate those random numbers. That's really fairly simple. So to basically switch from Gaussian to Levy, it's just really 3 lines of Matlab code if you want to. Yeah, so it's really, really easy to do. So there's a little bit of more work. Again, I don't want to go into the details. You take a uniform distribution, then you take an exponential distribution. That drawing from an exponential distribution is really easy because you can write down the cumulative distribution and invert it easily analytically. And then you have, again, sort of a box Miller-like transform that takes care of it. So it's the bottom line here, it's really easy to create these heavy-tailed random variables and figure out how they behave if you want to play with it. This is sort of the static picture. So now we want to make this whole world move. Yeah, so we now really know, well, we have a Gaussian we have a random variable, can be discrete, continuous, it can be Gaussian, binomial, and or alpha stable. What we now want to do is we want to move to the world of stochastic processes. And what stochastic processes essentially are, they are just time-dependent random variables. But before I go there, any questions up to this point? All good? All right. So when we look at stochastic processes, then again, the basic idea is very simple. We want to look at the collection of stochastic, of random variables that is now time dependent. And again, we somehow want the next random variable have to do something with the previous one. And technically, there is a whole framework that you need to set up in terms of filtrations, other things. Again, I'll just forget about this. What is interesting is, starting from the binomial distribution, what is the most basic construction that we can come up with to make our random variable time dependent that will lead to a reasonable continuum limit. And that's the construction of Brownian motion starting at random walks. Again, let me just stop for 1 second. Who has worked with Brownian motion before? A little bit? All right. So the way this works is, we have a time interval, let's say from 0 to 1. And what we do to this time interval, we just chop it into n pieces, okay? So then delta t just will be 1 over n. Now at each step, we can go up or we can go down. And we can go up with a probability a half. And then, of course, we can also go down with a probability a half. Okay. Now, what we still need to specify is how far we can go up at each step. So we can go up, we can go down, but I didn't tell you yet how far we can go up or down. And now I will present an argument why, if you see this for the first time, it might be a rather odd choice. Square root of 1 over n is exactly the right amount you want to go up or you want to go down. Okay. So let me present my argument. And again, if you haven't seen this before, this is really in this half a page, you have the essence of stochastic calculus. So if you see this for the first time, just ask any question that you might have. What does it mean to achieve a nice continuum limit? Well, I go up, down, up, down, up, down, up, down. I end up somewhere at 1. And then I go up, down, up, down, up, down. I end somewhere at time equals 1, and so on and so on. Now, if I look at this random variable Wn at time 1, what I would like to have is that the mean and the variance are independent of n. Because what's going to happen is, if this mean and variance, if they are independent of n, then I know that Wn will just have a binomial distribution. If the mean and the variance are fixed, then for n going to infinity, that binomial distribution will converge to a Gaussian. So how do I choose the scaling of the up and down jumps in order to make this happen? And now we need to remember that the variance is a quadratic quantity. So here's this how I can do this. So this formula means that xk can just go up or go down, +1 or -1, with probability half at each step. I sum those up. Now the central limit theorem obviously will guarantee that this is a binomial distribution that will become a Gaussian distribution. And now I can compute the mean and the variance of my random variable Wn at 1. Now, the mean is super easy because the mean I can just pull it through the sum. And obviously the mean of all these xk is just 0. So I end up with 0. The variance is a little bit more work, but it's fairly easy. It's a 2-minute calculation to show that for each of those xk, the variance is just 1. Okay. Now what happens is that if you now pull the variance through, this square root of 1 over n actually becomes 1 over n, simply because the variance of ax plus b is a squared times variance x. And now you see what happens. All these variances are 1. So I'm just left with 1 over n times n, and this is 1. And this is why this scaling here is exactly the right scaling that we need to have in order to create convergence. And this has funny consequences. So this, if you think what happens in this formula here for Wn1, you always add up what we also call a Brownian increment. And this 1 over n is nothing else but square root of delta t, yeah? So in other words, this means that what we add up is plus or minus square root of delta t, yeah? With probability a half. And usually if you go in time, you move with dt, yeah? But these stochastic terms, just because of the quadratic nature of the variance, to provide convergence, they need to move with square root of dt. And this oddity of the square root is the reason why, if you switch from regular calculus to stochastic calculus, there are a couple of new rules that you need to learn, like the Ito rule or things like that, simply because of that square root of dt. So what happens is, again, if you go up to time 2, you of course will have a little bit of a broader distribution. It becomes normal zero with mean 0, variance 2. In general, the variance of Brownian motion just increases linearly with t. Okay. Any questions up to this point? All right. So let's have a look how you actually would code this in Matlab. Okay. Can you see the Matlab screen? So what I do here is I actually simulate those Brownian paths simultaneously. Yeah. So I this second variable n paths, that just counts the how many Brownian paths I have. And what I do here, the whole evolution is vectorized. So in line 20, you see whenever I move forward, I move like, if I have 5 paths, I draw 5 random variables that are independent. That's the rand n path 1. And then just I move step by step, but I simulate all these paths simultaneously. And what is really important is, you see in line 20, there's this square root of dt. That's exactly the right scaling of the Brownian increment. So let's look at what happens if I actually execute this. So this goes up to time 1. So let's take 1,000 steps. Let's take 100 steps for first. And now I'm plotting this. And you can see this is sort of just a Brownian sample path where it goes up, down, and then somehow you get this path. Yeah. Now, if I choose 1,000 points, then obviously this becomes a little finer. But again, the statistics of the endpoint will not change. And of course, every time you take a different path, you get something else. Yeah? There are a lot of interesting mathematical properties to Brownian motion. Like, for instance, it will get further and further away from 0, but eventually it will always return to 0. Yeah, it's recurrent. That's what we say. And what we can do here easily is we can now add paths. So for instance, just have two paths. And you see, again, if you have 20 paths, you can sort of get a feel for how the variance is actually growing linearly in T. Yeah. So at the beginning, everything starts at 0, but as you go on, the knowledge of where your particle is, stochastic particle, starts to fade away. And again, at 1, you have a Gaussian distribution with variance 1, and at 2, it's variance 2, so it gets broader and broader and broader. Any questions? Now, this essentially, can you see the lecture notes again? So this allows you to start to look at a combination of stochastic and deterministic effects. And the way it works is, it's again really driven by the idea that when you move in the stochastic world, you need to move with square root of dt and not with dt. And one of the things that happens especially in the mathematical literature, is that people write stochastic differential equation in this funny way. They basically take the equation. So this equation has not yet any stochastic term, and they just rewrite it by multiplying this equation with a tiny dt, yeah, dt, yeah. So this is how they write it, to say that in calculus, what you do is, when you look at differential equations, what you need to do to solve the equation, if you think of step by step, you follow the tangent line. Yeah, this is what this means. Yeah, this is just follow the tangent line. F is your derivative, so you just follow the slope of the tangent line to get your next point. Now, if you add noise, then in math world, the preferred way of writing this is really this notation, where you basically have the deterministic part here, and then you remember where your noise comes from. It comes from Brownian motion. And what this means is that at each step, all you need to do is you need to draw a random number and scale it with square root of delta t. And this is how you move on. And this is how you can combine deterministic and stochastic effects. So if you write this as a numerical scheme, this is what you end up with. You simply, for the deterministic part, you just follow the tangent line and scale this with delta t. And for the stochastic part, what you do is you draw a random number and then you scale it with square root of delta t. And so if you recall the definition of Brownian motion, then this R should be +1 or -1 with probability 1/2. In many real-world applications for faster convergence, you substitute this by a normally distributed random number, and you can actually show that the central limit theorem provides sort of the right correspondence between these things. So this is often sort of a numerical cheat. Instead of putting in +or -1 with probability 1/2, you actually just plug in a normally distributed random number in order to figure out what's going on. And if you look at carefully at the Matlab code, then that's exactly what happened here. Yeah. In line 20, it's rand n, and rand n is just the command in Matlab to draw a normally distributed random number. So these kind of, there are more general versions of this. So what I just did is I just added, this is all one-dimensional, and I'm just looking at additive noise. Obviously, you can generalize this. You can have this in many dimensions, and you can also add multiplicative noise, where your sigma actually depends on the process. All these things can be done. There are additional mathematical complications if you do this, but all these things can be taken care of. Also, just to mention, there is a strong relationship between stochastic differential equations and associated partial differential equations, in particular the Fokker-Planck equation. That basically this idea that stochastic equations and partial differential equations are strongly related. And that's one of the things that we will exploit and explain in a few minutes. There's another equivalent formulation of this in terms of path integrals. And in particular, if you have very small noise, this is a formulation that can lead to really interesting results. That's one of the things that I've been working on in my research, also with Tobias and Eric van den Eyden over the last, I don't know, 10 years, Rainer Grauer in Bochum as well. And yeah, sort of this world is very interesting because you have stochastic system, partial differential equations, and the path integral formulations. And there's a lot of structure and a lot of interesting ideas that you can look and exploit. And sometimes to understand one thing in one world, you just need to go to the other world in order to figure out what's going on. One of the interesting points is that it is now really easy to go to something that only recently, I would say in the last 10 or 15 years, has come into focus. These are Levy-driven processes. Remember, we were talking earlier about those alpha stable random numbers. Now, immediately there's the idea, what happens if I actually use those random numbers in order to drive my motion? So in other words, I look at the same stochastic differential equation that I have here. I look at this stochastic differential equation, but now what I want to change is I want to change the type of noise that I want to use to drive my equation. Now, for Brownian motion, this was sort of easy. All I need to do is follow this rule. I take a random number that's normally distributed, and then I multiply it with square root of delta t in order to get my right scaling. But what if I want to actually use a Levy process, a process based on those alpha stable variables? And with a little bit of work, this is actually sort of super simple. All you need to do is, instead of the Brownian increment, you use the associated Levy increment. And see the scaling of dt for alpha equals 2 is square root. So the general scaling is just 1 over alpha. Yeah, so you just need to get the scaling right, and you need to be able to draw from an alpha stable distribution. But we know how to do this because we have a Box-Miller-like algorithm that allows us to do this actually fairly easily. So let's have a look. You should be able to see the Matlab again. Can you see the Matlab? So the alpha in the nodes is now called mu in the code. Yeah, so it's the same thing. It's just called mu. Yeah. And again, for now, let's focus on alphas that are between 1 and 2. That means that those alphas have a mean, but they don't have a variance. Okay. So this code compares just for one path, Brownian motion and Levy motion. And it's really super simple. For the Levy, it just follows exactly this idea. You see in line 24, we just draw a random variable in line 23, psi, that is, we draw it according to our alpha stable distribution. And then we scale it correctly with DTM. And DTM is exactly what you think it should be. DTM is just DT taken to the power 1 over alpha or 1 over mu in the language of this code. And then just to get a feel for what is happening now, we also simulate Brownian motion. We only simulate one path here. So this is like really simple now, yeah. In DTS is just square root of delta t, and R is just standard normal random number, okay? And then we save the results and we can look at them. Any questions regarding this code? So part of this whole spiel here is to advertise that getting into the idea of stochastic differential equations and doing some numerical simulation where you compare equations driven by Brownian motion and driven by Levy processes is actually really simple. Yeah, in the easiest case, it's just a few lines of code. You only need to know how to generate those random numbers, and you also only need to know how to scale everything appropriately. And this is how you can do this. All right. So now we are going to look at the picture of what is actually happening here if we compare the sample paths that arise from these Levy processes. So again, let's just take 1,000 steps. This time we go to time t equals 2. It doesn't really matter at all. And let's go for an alpha 1.3. Okay. This is the Brownian motion. Nothing too exciting. Just different Brownian motion. And now let's compare this to the Levy motion. Let's do a couple of these runs to get a feel for. So if you look at that picture intuitively, what does the Levy motion have that the Brownian motion doesn't have? Just phenomenologically.
It has some rare event that throws it like far away from, and otherwise it's just like the Brownian motion.
Absolutely, it has a couple of these jumps in there, and these kind of combined models, they are in general, those models are called jump diffusion models, have been, you can probably guess in which field they have been really, really very successful and heavily researched. Can you guess the field? In financial mathematics. To a point actually where now things come back. You know, it used to be that all the mathematicians and physicists, they go to Wall Street. After 73, the Black-Scholes paper was, and there was this huge flux of a lot of really smart people starting to work on something where one can have a long argument on how useful this is for society. But actually, over the last 15 years, there was quite a bit of research driven by this activity, and sort of there's a little bit of things coming back in terms of really understanding the fundamentals of these kind of processes. And again, in many fields, these sort of jump diffusion processes recently have become really into the focus. So to not only look at systems that are driven by Brownian motion, but also driven by more complicated noise, where in some way at the microscopic scale, when you set up your problem, you already build in exactly what you're saying, those rare events and those heavy tails. And again, part of this tutorial is just, and again, when I earlier said, you want me to email you the codes or something like this, just send me an email. Probably just put my, it should be probably everywhere, but I could just put it into the chat again. And
Yeah.
I'll be
Can
totally
I ask
happy
a
to
question?
share. Please, yeah.
Yeah. So you said that in the simulation we are using the R is normally distributed, right? And not just plus or minus one. So if the R was just plus or minus one, I would not have those jumps, right? So
For the Brownian motion.
And for the Levy motion, you always like use this normally distributed.
The Levy case. Maybe there's a different way of doing this, but this is usually what people are doing.
Mhm.
All right. For the next step, I want to go back to the world of Brownian motion and talk a little bit about the relationship between stochastic differential equations and partial differential equations. So the idea is that if you look at a stochastic process, you can look at these paths that we have been looking at, but of course you can also look at the time evolution of the underlying probability density. And that is a deterministic quantity. Yeah, because the stochasticity is just encoded in the fact that you're looking at a probability density. So it's a fairly quick calculation. Again, I probably at some point should mention some of the references. There's this book, Gardner, Handbook of Stochastic Methods. It's not really a textbook, but it's a really useful reference. Like, for instance, if you're interested in this particular transition, how do I get from a stochastic differential equation to the Fokker-Planck equation? You just open Gardner and it will actually very nicely explain these things to you. So there's a correlation, there's a correspondence, and what happens is that this stochastic term actually appears as a diffusion term. And intuitively, that sort of makes sense because that is sort of what stochasticity is. Yeah, it diffuses and drives particles away. If you do this with Levy terms, things get much more complicated. You end up in, again, a field that only recently has sort of started to flourish. That's the field of fractional partial differential equations, yeah, where your derivatives are not integers, but you take a derivative like the of order 1.5, yeah, and how to do this. So again, a really interesting field directly related to these Levy motions. In the simplest case, Brownian motion turns out, so Brownian motion means that you simply have f equals 0 here for Brownian motion. And it turns out that you just have the heat equation. And you probably know that the heat equation is just solved by the heat kernel, which, if you again think of your particle being at time 0 at 0, relates into the initial condition for the probability density simply as a delta function at that time. And what happens is then that the derivative, the second order derivative, will just start to smoothen out your initial profile. Yeah. So at time t equals 0, your probability density is just peaked around 0, and then it just starts to become broader. And that's exactly the corresponding picture from the PDE world that we saw in the Matlab simulation earlier. Yeah, so these were all the paths. Now, if you think of this as distribution, it means that the width of the distribution just increases linearly with t. Yeah, well, the variance increases with t. And that's exactly what this formula is telling you. That, sorry, there are a couple of typos, obviously. Sorry. This is x squared and this is 2t. I apologize. This is the correct version of the heat kernel. Yeah. So obviously it's Gaussian in x, but then the variance, the sigma squared, is just given by t. Yeah. So gross as t. And so this correspondence between stochastic systems and PDEs goes a long way. So over the last 50 years, both fields have really influenced each other in sort of incredible ways that you can prove a certain statement in one field and then it carries over to a statement in the other field, and I think so. One second, I just need to organize my. All right. So one interesting next step is to extend this idea to two-dimensional systems. And this, again, not going through all the proofs here, is fairly simple. So here I just wrote down two stochastic differential equations, and there's a deterministic term here, V1 for the first component, and there's a deterministic term here, function for the second component, V2. And then there are stochastic terms given by the two independent Brownian motion. And here, for a change, I just wrote it down sort of how the physicists write it down here, where they divide the whole equation by dt. Now, this equation has an interesting interpretation because it's an example for a fluid equation. And this is sort of how you now connect the stochastic world to fluid systems. In fluid systems, the idea is that the velocity field that is specified by the fluid is incompressible. That means that the divergence of V is 0. So if you write down the associated two-dimensional Fokker-Planck equation, what you get is you get the so-called advection diffusion equation. Yeah, so there is an advective part. What is this part? And then there is a diffusive part. And this, again, the advective part is, for instance, if you think of C as the concentration of a dye that you put into a fluid, then the dye particles are advected by the fluid according to the velocity field that is specified by the fluid. But that's not the only effect. The dye also diffuses. And this diffusion part is modeled related to the stochastic part. And that is modeled by kappa and the Laplacian. And typically, what we are interested in is the case where kappa is really small. So this is sort of the really difficult case. Because what happens is then whenever you have a small parameter in front of the highest derivative, your differential equation becomes singular. And that causes a lot of problem. It's sometimes hard to get analytical results, but it's also numerically, it's difficult. So ideally what you have in these situations, you have very small diffusivity, a lot of points, and a time step in your numerical procedure that is still manageable. And one sort of simple example where you can actually calculate the solution analytically is where V1 and V2 are constant. Then what will happen is that the concentration just will basically move at a constant speed, and it will be diffused at the same time. So for instance, you start with a small Gaussian blob here. It will just be advected, and it will go bigger and bigger because of the diffusion. Things become much more interesting if you make those velocity field time dependent. And a standard example is of this time dependence is a so-called Taylor-Green flow. What is essentially given by this velocity field here. And what it does, it basically just rotates the way we'll see how the numerics are set up, just in 4 different parts, and it just rotates the fluid. And then if you go a little bit further to sort of see some real fluids, what you can do is you can put in some time-dependent perturbation. And what is really happening if you have a background in dynamic system or classical mechanics is the original unperturbed flow has 2 separatrices. And what is happening is that the perturbation will sort of destroy those separatrices. And then you get sort of the feeling that you are in fluid world. So let me just show you a code to get a feel for what kind of systems you can already describe with this sort of, in some way, fairly simple PDE model. Again, once you perturb those flows, it's usually very hard to actually get analytical results. There's some calculations that can be done, but it's usually fairly difficult. All right. Can you see the Matlab again? So this code just takes an initial condition, which is fairly simple. In one side it's up and the other side it's down, and then it just starts to solve the advection diffusion equation. This is just it's a semi-spectral scheme. It's using an Adams-Bashforth. I don't have time to go into the details of how to do this numerically, but again, by all means, if you're interested or you want more information or you want to have the code, just email me and I'll be happy to to give you some more insight. So the again, all these codes are fairly short. Yeah, this has like 79 lines, and there are some comments. These are not big codes. So if you look at line 67, this is basically where you choose the parameters for the velocity field. And if I set epsilon equal to 0, the velocity field of the fluid is just the basic Taylor-Green flow: sine x, cosine y, negative cosine y, sine y. Remember, things need to work out because the flow field needs to be incompressible. So now if I run this, what I really would like to do is would like to have n, that's the number of points I have on one side. I would really like to be that number to be large. So you see the fluid has slightly different vortices in each quadrant, and it starts to move I mean, one is negative, one is positive. It sort of starts to move the die. And right now you can see the picture moving. So right now it's a little unclear what is actually happening, but in a minute or two, you will sort of see that the flow is really sort of in 4 different compartments. And again, they are basically separatrices in the deterministic picture. So that just means there's very little interaction between those regions that are separated in phase space. And you will, again, now you see the die gets a little bit detached. And this is not so super exciting because I chose actually only 32 points. Yeah, so it's a little, and now you sort of can see that it starts to slowly swirl. Let me try to speed this up a little. I think I can do this. So the idea is, if I choose a larger time step, I might get into trouble with what is called a CFL condition. Let's see whether my code still will be stable. Now it's 10 times as fast. But with 32 points, I should be fine. So the idea is, the higher resolution you have in these simulations, the smaller your time step needs to be. Now you can see how these regions of the phase space are isolated. Yeah, so there are like 4 vortices. Just in each region, there's 1 vortex. Yeah. Now, if we start to perturb this flow, let me see whether I can still get away with the same. Now I put on a time-dependent perturbation. And I probably should restart this. Now there's a time-dependent perturbation, and now you see, because of that perturbation, the separatrices are not separated really anymore. We sort of start to wiggle on those separatrices, and now you can really see that this whole picture looks a little bit like a fluid system. Yeah. You can get much nicer and crisper pictures, but again, what you usually need to do is you need to have less diffusivity, more points, and then you need to have a much smaller time steps. And this is why these kind of computations are computationally challenging in general. All right. Is everybody okay if we go like 10 minutes over? Is that okay for everyone? Sorry about this. It always takes longer than I've planned. All right. Let's go back to the lecture notes. Can see the lecture notes again. So now this is where the real fun starts. See, in this advection diffusion equation, the idea was that V1 and V2 are the velocity fields that are given, specified by the fluid, and C is the concentration of the dye. If you want to understand how the fluid itself is moving, then the idea is that a fluid particle is actually advected by the fluid itself. So what you need to do is the equation becomes nonlinear, and this is how you end up with the Navier-Stokes equations. Yeah, so this is really where now the advective term is the fluid itself, and that obviously leads to a nonlinearity. And these equations are really hard, especially in 3D. And there's a little bit more, a tiny bit more we have to say. The fluid needs to be incompressible, meaning that the divergence has to be, the divergence of U is 0. And in order to maintain this incompressibility condition, we need to introduce one more function. You can think of this as sort of the Lagrange multiplier that makes sure that that constraint is satisfied. That's the pressure here. Okay, and this is how you end up with Navier-Stokes equation. So you can think of that now the fluid is advecting itself. And these equations are really difficult to solve. And one idea was in the past that to figure out whether we can write down a really simple toy model and then sort of practice on this toy model, sharpen our tools, and then take those tools to Navier-Stokes. And one of those toy models is the so-called Burger's equation. Yeah? You see, the Burger's equation is just a 1D equation. It has exactly the same structure as the Navier-Stokes equation. There's no incompressibility, there's no pressure, but it has an advective and a diffusive part in here. So in the past, a lot of people have advocated to use Burger's equation as a toy model for Navier-Stokes. And so this has been heavily debated whether this is actually reasonable. Some people say if you say I'm looking at turbulence in Burger's equation, you should not call it turbulence, you should call it Burgerlence. But the most appropriate idea about this is probably one of the ideas that once I heard from Uriel Frisch, who has worked in this area for I don't know how many years. This idea that this Burger's equation is sort of a negative paradigm. If you have an idea how to attack Navier-Stokes, why don't you try it on Burger's? And if it doesn't work on Burger's, it probably won't work on Navier-Stokes. If it works on Burger's, there's no guarantee at all that it will work on Navier-Stokes. Most likely not, because most likely nothing will work. But as a way to discard ideas, Burger's is perfect model for turbulence. Anyways, there are a couple of really interesting features about the Burger's equation. It actually has a direct cascade. So what you do is, often in these systems, you look at the energy depending on K, where K is basically the wave number. So if you think you Fourier transform your system, And then you can sort of look at how the energy is distributed over the different scales. And what happens is that in Burgers and 3D Navier-Stokes, you have a direct energy cascade, which means that if you inject energy on large scales, nonlinearity transports this energy down to small scales. And at small scales, diffusion kicks in and dissipates this energy. So in this sense, 3D Navier-Stokes and Burgers equation have actually a certain similarity. 2D Navier-Stokes is different. In 2D Navier-Stokes, we have an inverse cascade, which means that energy from smaller scales is transported to larger scales, which makes this also a really interesting topic. And in certain systems where, for instance, you have a lot of layers, like in the atmospheres, sometimes these kind of ideas play a huge role. That's also one of the things that you will see on Friday. Another feature of Burgers that makes Burgers very different from Navier-Stokes is that it's integrable. So there is a transform called the Kohlhoff Transform that's really famous. So both Kohl and Hoff got really famous because of this transform, because they sort of rediscovered it. Later, it turned out that I think it was an exercise in one of the fluid dynamics books at this turn of the century, where obviously somebody already knew this a long time ago. Burgers equation, no matter how small viscosity nu is, as long as you have some viscosity nu, can be transformed into the heat equation. So essentially it's integrable and you can entirely solve it. And people believe that that's not the case for Navier-Stokes equation. And what's then very often happening, and that's again one system that I've worked on a lot, also together with Tobias, is to start to look at what you see here. You take a PDE and then you make it noisy. Yeah. So now you go to the next step. You have your partial differential equation, and then you make it a stochastic partial differential equation. And one of the motivations is that maybe if you look at a really fully developed turbulent system, that then sort of the small scales, they are like all noisy and they behave like noise. But this idea, it goes a long way, but it doesn't go as far, so far, as we would like to go it. In fact, in some way, classical turbulence and its entire, if you really look at the essence of it, is still maybe the last unsolved classical problem. Yeah. Anyways, just one small remark regarding 2D Navier-Stokes. Again, in 2D Navier-Stokes, they do have an inverse cascade, so energy flows from smaller scales to larger scales. And in 2D, again, it's fairly easy to simulate. You can almost take the same code that I took for the advection diffusion equation, and you just need to modify it a little bit in order to convert it into a 2D Navier-Stokes solver. Usually 2D Navier-Stokes, what you do is you don't look at the velocity field itself, you look at the vorticity. So the vorticity you get if you just look at the Navier-Stokes equation, up, and then what you do is you just basically take the curl. And if you take the curl, again, in 2D, you need to think a little bit, do a little bit vector analysis. This is sort of the equation that you look at. And as the last picture, let me just show you some code there. So this is the 2D Navier-Stokes. So this 2D Navier-Stokes code just starts with a random initial condition of the vorticity. So it basically places into
I think we can't see the Matlab.
Thank you. Thank you so much. Ada, can you see the Matlab now?
Yeah.
Thank you. So again, let's take, I think we can probably do 128 in a couple of steps. And what it does is it just starts at a random initial condition, and then it just solves the 2D Navier-Stokes equation. And yeah, you really need at least 128, and you see it's not very fast on this laptop, but you can probably see a little bit that things are moving around and they are sort of slowly moving to larger scales. Yeah, so this is not only diffusion, it's really that you have this inverse energy cascade that yeah, smaller scale energy in smaller scales actually moves to energy in larger scales. Yeah, and you see it's not very fast, but hopefully it sort of illustrates the idea. I'm already a little bit over time, but this was sort of the ideas of today's tutorial, to sort of give you a little bit of the different aspects, to see how, what if somebody now writes down Burger's equation with Levy noise, that you have an idea of where this comes from and why it's interesting if you see 2D Navier-Stokes, or people use terms like direct cascade and inverse cascade, that you have a couple of pictures and sort of ideas of what is sort of the background and why it is sort of interesting to look at these things. Are there any questions from your side about anything that we talked about today? Maybe stop sharing the screen. So I hope that was useful for you and you enjoyed it a little bit. If again you have any follow-up questions, or you'd like I don't know, the PDF of those notes, or you like the any of those codes or all of the codes, just shoot me an email. I'd be more than happy to share those things with you. And if you then have any follow-up questions, like how was this done in Matlab, again, this can be always the beginning of a conversation. All right. Any questions, comments? If not, then well, thank you so much for attending the tutorial, and I hope to see you all on Friday.